Hi, I'm Aditi Netwewala. Today my talk is on inhomogeneous magnetic landscape in lanthanum aluminate strontium titanate nanostructures. Before starting, I would like to thank Vannevar Bush Faculty Program for supporting this work. So, we work in the field of correlated nanoelectronics, which basically arises from two well-established fields. On one side, we have the correlated electron physics, which is mostly studied in bulk materials and shows interesting properties like superconductivity and ferromagnetism. On the other side, we have semiconductor nanoelectronics, which allows us to have single electron control and thereby study the quantum properties of the system. At the interface of the two is the oxide heterostructures, which allows us to have single electron control like the semiconductor systems, but we also see rich correlated electron physics at its interface. So it's a very interesting system to study. We are interested in this particular heterostructure called lanthanum aluminate strontium titanate. So back in 2004, it was shown that when we have a thin layer of lanthanum aluminate stacked on strontium titanate, a high mobility 2D electron liquid is formed at the interface. Further, if the thickness of the lanthanum aluminate layer is 4 unit cell, we can tune the 2D from the insulating to the metallic regime. So over the years, several other properties were discovered like superconductivity, magnetism, and tunable spin-orbit coupling. Now both lanthanum aluminate and strontium titanate are non-magnetic band insulators. So it was very interesting when magnetism was discovered at the interface and it was studied in depth. One very interesting property was observed when mesoscopic Hall bars were etched at the LaAlO3 interface. The Hall resistance showed a nonlinear nature, and this was termed as anomalous Hall effect. Later, this nonlinearity was attributed to the multiband nature of the 2D electron liquid. So at lower carrier density, the DXY bands were supposed to be occupied, and as we increase the carrier density beyond the Lifshitz transition, the DXZ-YZ bands are believed to start getting occupied, and this has been attributed to produce the nonlinearity. However, this theory is not valid in the small field regime. So if you look at the plot, the field at which the nonlinearity takes place is HC parallel, and it diverges at around the Lifshitz transition. So around the same point, another very interesting property was observed in single electron transistors at the LaAlO3 interface, which was electron pairing without superconductivity. So electron pairs were observed till a critical pairing field BP, which can be much greater than the superconducting transition field, and this pairing field can also be tuned with the carrier density. Over here we have a side gate, and it is very interesting if you note these two plots that they show very similar characteristics. Both the nonlinear field and the pairing field can be tuned with the carrier density, and they have a similar trend as a function of the carrier density. It increases with the decreasing carrier density. So this led us to think that whether there can be a possible relationship between the two. And but this was studied in mesoscopic systems, whereas electron pairing without superconductivity is seen in ballistic systems, and these are single electron transistors, so we had to combine the two. In our lab, we have developed this technique of writing nanostructures called CAFM lithography. So we have a thin layer of lanthanum aluminate on strontium titanate, and we make interface contacts by depositing titanium gold electrodes. We then use a conductive AFM tip to write a device. So when we apply a positive bias to the tip, it protonates the surface, which attracts electrons to the interface, and this is like a local modulation doping process, and the structures can be as small as 2 nanometers. And on the other hand, when we apply a negative bias to the tip, we can erase the protons, and we use this technique to create our tunnel barriers. It is worth mentioning that there is no physical modulation of the interface, and we can repeat this process as many times as we want. So it's a very powerful technique for writing nanostructures at the interface. And we used it to first create quasi-1D ballistic electron waveguides at the LaAlO3 interface. So we have the LaAlO3 nanowire, which can be tuned with the side gate whose chemical potential can be tuned with the side gate. And when we plot the longitudinal conductance of this system as a function of the chemical potential, we see E square over H quantization plateau with a scattering length of around 20 micrometers. And if now we take the derivative of this, then we get the rich subband structure of the system of the waveguide, and it was theoretically verified that we have these waveguide modes. Also, these systems show electron pairing without superconductivity, so there is ballistic pair transport to and it has been measured till fields as high as 11 Tesla. So for this case it's around 9 Tesla. We see that the 2E square over H plateau becomes around 1. So so we achieved the first part, that we have we have ballistic pair transport in these electron waveguides, but how do we combine the Hall measurements with it? So the very first thing which comes to our mind is a cross-shaped electron waveguide, that is a nanocross. So it is an 8-terminal device with a 1 by 1 micrometer central segment and 4 highly insulating barriers, transparent barriers, which allows us to tune the device with the help of the side gate. So we write the device using CFM lithography and cool it in a dilution refrigerator and take magnetotransport measurements, and the multi-terminal nature allows us to take both longitudinal and Hall measurements. So we first look at the longitudinal measurements, and so these are the 6 configurations in a nanocross, and we see that we can group it into 3 sections on the basis of the distinct transconductance spectra. And what is very interesting is that there is an inhomogeneity observed in the pairing field for each group. So for group 1, we see that the pairing field is around 3 Tesla. For group 2, it is greater than 8 Tesla. And for group 3 also, it is greater than 8 Tesla. So we do observe electron pairing without superconductivity, and we see an inhomogeneity in the pairing field. So next, we wanted to see how the Hall measurements look. So we took one particular configuration and we saw the Hall resistance for it, and initially it was not exactly anti-symmetric, and it had an intrinsic offset. That is because the longitudinal measurements can easily couple with the Hall measurements because of the nanocross geometry. So we anti-symmetrized it, and what we get is a beautiful nonlinear Hall effect. So now we wanted to analyze that at what field does this nonlinear transition occurs, and so we took the slope and we plotted it as a function of the field, and we see that there are some features over here, and we can divide this region into 2 distinct regimes. So this region where we have the flat slope, flat region denotes the first slope, and then the increasing region denotes the second slope. So if you notice, this is also around 3 Tesla, which is exactly or very close to the pairing field for group 1, where the electrons transition from the paired state to the unpaired state. So we wanted to understand that why would it be related. So the first thing which we see is that the subband structure in these cases can be divided into 3 distinct regions. We have the paired state, we have the unpaired state which is not completely spin polarized, and we have the spin polarized unpaired state. And each state will have a distinct spin polarization. So we see that because this is not a sharp transition from the paired to the spin polarized state, we have a non-linear spin polarization as a function of the field, and this would add to the non-linearity in the Hall measurements. Further, we have noticed that there is an inhomogeneous subband structure, and so this inhomogeneous subband structure will give an inhomogeneity in the pairing field PP, and this would further add to the non-linearity in our measurements. So altogether, this gives rise to an inhomogeneous magnetic landscape in the nanocross, which produces the anomalous Hall effect. So to summarize, we studied the transport properties of a nanocross, and we basically concentrated on the pairing mechanism and the Hall measurements, and we found that they are correlated. And we attribute this to the nonlinear spin polarization because of the paired and unpaired states, and the inhomogeneous subband structure, which gives rise to an inhomogeneous pairing field. So this together gives rise to an inhomogeneous magnetic landscape, leading to the anomalous Hall effect. Thank you.